Hi everybody, in this video we are going to start our discussion of what our textbook calls special limits. And these are a couple of limits that are going to be really important to us moving forward over the next couple of chapters. And the first one is that the limit as alpha approaches 0 of the sine of alpha divided by alpha is equal to 1. And we can verify this by looking at a table, but this is about doing the proof and making sure that we have put this on solid ground. And so what I'm going to start with is, as you can see here, I have a unit circle and I've marked the point 0, 1 on the unit circle. And I'm just going to draw an angle in standard position, which I will name alpha. This point right here, you will recall, is the cosine of alpha, sine of alpha. And then I'm going to look at three different things that are in this picture. The first one is the triangle that is inside of this unit circle. And so let me just draw that triangle right here. It looks about like that. It has an angle of alpha. The base of that triangle is 1 because it's the radius of the unit circle. And the height of that triangle, well, the height of that triangle is going to be the y coordinate that is right here. So the height would end up being the sine of alpha, which means that the area of this triangle would end up being 1/2 the base, which is 1, multiplied by the height, which is the sine of alpha. Okay, second thing that I want to look at is this arc, the area of this sector. And so you'll see that I drew this line here, giving me that triangle, but now I'm talking about that slice of the circle. Like if this was a pizza, that would be a slice of pizza. And that is going to end up being this, this area of a sector. So it looks almost the same as that triangle, but it has got a rounded edge. This is going to be 1, and this is going to be 1 because those are both the radii, and those are both the radius of the circle. And the area of a sector is given by 1/2 the radius squared multiplied by the angle. And what would have to be the case is that since the area of the sector has got this little tiny slice that the triangle doesn't have, is that it has to be the case that this area of the sector is bigger than the area of that triangle. And so I've got this inequality. I'm going to put that it is less than or equal to, because the smaller that alpha gets, the closer that these two things will get together, or be together. And when alpha becomes 0, these two things would end up being exactly the same. And then the last thing that I'm going to do is to draw a line that is tangent to the circle and go up to where that the terminal side of the angle would be on the outside of the circle. And then I want to look at the area of this bigger triangle. And so clearly I can see that that area of the bigger triangle is going to be bigger than both of these two things. And then if I drew you a picture of that triangle, it looks about like this. And the base is going to end up being 1. And then the height of this triangle, well, let's see, if I think I would get that this would be the tangent, right? So if I just let that be y, then the tangent of alpha would be y divided by 1. So the height of that triangle is y, which means that the area of the triangle would be 1/2 the base, which is 1, times the height, which is the tangent of alpha. So now I have this three-sided inequality, and I'm going to clean things up a little bit. I've got a bunch of 1s in there that I don't need. So I'll rewrite this as the sine of alpha divided by 2 is less than or equal to alpha divided by 2 is less than or equal to the tangent of alpha all divided by 2. And this is going to have to be true for all angles of alpha that are in between 0 and pi over 2. Now, because I've done this before and I know how to do this, I am going to multiply all three sides of this inequality by 2 divided by the sine. So multiply all three sides by 2 divided by the sine of alpha. What's going to happen? When I multiply sine of alpha divided by 2 divided by the sine of alpha, that's going to all cancel and give me 1. And then here, the 2's are going to cancel, and I'm going to get alpha divided by the sine of alpha. And then lastly, I will get the tangent divided by 2. Let's see, so the tangent is the sine of alpha divided by the cosine of alpha. So it would be 2 divided by sine of alpha divided by 2 cosine of alpha. And I multiply it by 2 divided by the sine of alpha. Well, the 2's are going to cancel, and the sine of alphas are going to cancel. And this is going to end up being 1 over the cosine of alpha. So that's just a little bit of simplification of the trig formulas. And so now you can begin to see this thing take shape. I've got alpha divided by the sine of alpha. My original question is I want to look at the sine of alpha divided by alpha. So I'm going to flip each one of these things over. And if you recall that when you flip both sides of an inequality over, so like let's say that I had the number 4 and the number 3. So 4 is bigger than 3. But if I flip them over to get 1 over 4 and 1 over 3, now 1 over 3 is bigger. So you're allowed to flip over an inequality, both sides of an inequality, as long as you flip the direction of the inequality as well. So when I flip over 1, that's going to become 1. And then this is going to be bigger than or equal to the sine of alpha divided by alpha, which is going to end up being bigger than or equal to the cosine of alpha. I'm just going to rearrange the direction. We tend to write things going from smallest to largest and left to right. So if I put the cosine of alpha over here, then that would be less than or equal to the sine of alpha divided by alpha, which would be less than or equal to 1. All right, so let's rewrite this on a new piece of paper here. So I have got that the cosine of alpha is less than or equal to the sine of alpha divided by alpha is less than or equal to 1. And now what I'm going to do is take the limit of all three sides. So I'll like the limit as alpha approaches 0 of the cosine of alpha, which is less than or equal to the limit as alpha approaches 0 of the sine of alpha divided by alpha, which is less than or equal to the limit as alpha approaches 0 of 1. So the limit as alpha approaches 0 of 1, obviously that's going to be 1 because 1 doesn't change. Here, as alpha approaches 0, the cosine of alpha, well, that's fine, right? The cosine of 0 is 0. There's no issues with, or the cosine of 0 is 1. There's no issues with things being undefined. So that limit is going to have to be 1. And so when I simplify this, I get that 1 is going to have to be less than or equal to whatever this limit as alpha approaches 0 of the sine of alpha divided by alpha, and it's going to have to be less than or equal to 1. Well, the only way for something to be bigger than or equal to 1 and less than or equal to 1 is if that limit is going to actually be 1. So that is going to imply that the limit as alpha approaches 0 of the sine of alpha, as alpha approaches 0 of the sine of alpha divided by alpha, sorry, let me get that to look right, sine of alpha divided by alpha is going to end up having to be 1. What we are taking advantage of here is called the squeeze theorem. Because I took this value that I was looking for and I squeezed it in between two other limits and got them both to end up approaching the same thing, so that this limit had to end up being squeezed to be exactly 1, since it had to be in between 1 and 1. All right, the second special limit that we will use a bunch of is that the limit as x approaches 0 of 1 minus the cosine of x divided by x is equal to 0. And so we'll look at a proof of this one as well. And this one is going to take advantage of the one that we just finished. So I'll start with the limit as x approaches 0 of 1 minus the cosine of x divided by x. And then, because I've done this before, I know that this is going to help me if I multiply the top by 1 plus the cosine of x and multiply the bottom by also 1 plus the cosine of x. So what's going to end up happening? Again, just doing a bunch of algebra. This will be the limit as x approaches 0. In the top, that is going to be 1 minus the cosine squared of x. And in the bottom, it is x times 1 plus the cosine of x. And then that, up on the top, I've got sine squared. So this will become the limit as x approaches 0 of the sine squared of x divided by x times 1 plus the cosine of x. And then lastly, again, I've done this before, that's how come I know this will work. The limit as x approaches 0, I'm going to take one of those signs, sine of x, and divide it by x, and then I'm going to multiply that by the other sine of x divided by 1 plus the cosine of x. So now this is a limit of a product, which, as long as both limits exist, is the product of the limits. As x approaches 0, sine of x divided by x, that is equal to 1. As x approaches 0, in the denominator here I get 1 plus the cosine of 0. Cosine of 0 is 1, so in the bottom I get 2. On the top I get the sine of 0, which is 0, so all of this ends up going to 0. And just to emphasize the point, I'll write that it's 0 divided by 2, and that's totally fine, right? So 0 divided by 2 is 0. Multiplied by 1, this limit has got to end up being equal to 0. So these proofs are really important because these limits are going to be very important to us. They're going to come up in a lot of homework problems in Chapter 2, and then they're going to be really key things that we're going to use an awful lot of in Chapter 3 to prove some very, very important results.